That was somebody. I'm going to give you credit for it. It was Connor. Thank you, Connor. Standard normal curve. The blue one up there is the standard normal curve. That's the one when you guys use the normal in 243, or if you guys use the charts in 244 or in 243, whatever. That's the curve you're working off of. The red one in there, the red one is the T distribution that Gossett came up with. How is the red one like the blue one? How is the red one like the blue one? It's bell-shaped. He developed it to be symmetric because he said, all right, central limit theorem guarantees me sampling symmetry. I better include that. But he made, how is it different now? How else is it similar? It's bell-shaped and it's also has the same average. Thank you, Brent. Has the same average. It's centered on the same value. That was important. They're both centered on 0 because that means we can normalize them to 0. And that's important for consistency. Good. Thank you. So they're both bell-shaped, both centered on 0. How are they different? How is the red different than the blue? Wider. I hear a vote for wider. See how it's not as tall? It shrinks down. Well, what percent area is under either of these curves? This is probably too easy of a question. You're probably overthinking it. When you shade under the curve, the entire thing, including the asymptotic tails, what percent have you shaded? 100%. So the red curve also has 100% area under it. So since we dropped the top from the blue curve to the red curve, what has to change elsewhere in order to maintain the 100%? It's got to spread out to make up for that area. And what happens is the tails get fatter. Now, why would that be good for small samples? Why would that be good for small samples? A small sample is more or less certain to be precise. Much less, right? Depending on how small, much less. So you have to increase your margin, right? You have to increase your margin to ensure that you trap it with a small sample. So what you're seeing is between -2 and +2 on the blue curve is what percent of our area? 95. That's 95, right? You can see pretty clearly that that's less than 95% on the red curve, can't you? We'd have to move, I don't know why I'm doing that. I'm going to drop this thing in my head. We'd have to move out this way, yes? How far do you think we'd have to move? Until we got 95 on the red. Maybe that's too far? Maybe somewhere in here? Maybe. So, pretty far out, right? This is why we need a different multiplier for margins of error when you're dealing with averages. You need to scooch the multiplier out to keep the 95% confidence. Because depending on your sample size, 95% confidence won't be gotten with a multiplier of 2. That might not be enough confidence. It might not be fair right now, but is that believable? If you believe the shape of that curve to be what it is, and trust me, I built it over here painstakingly. If you believe that shape to be true, can you believe the fact that since the head drops, we have to move further out to trap 95%? Is that a fair assumption? If you can buy the curve, and I don't expect you to buy the curve right now. It took me a while to buy the curve. It's not the kind of thing I want you to get in 5 minutes. But now here's the really, really cool part. If you increase your sample size, watch the red curve. What's happening to the red curve as your sample size goes up?
It's getting closer to the same.
It's asymptotically limited to the normal distribution. Watch. As soon as we get up to a sample size of 30, which is my Del Taco half-pound bean and cheese burritos, can you even tell them apart? Not good answer. Not really. Good. There is a difference. Of course there's a difference. You can look at this, and there is a difference there. There for sure is. But it's so close that it's almost negligible. It's so close it's almost negligible. So for years and years and years, there was this magical number attached. As long as you had 30, we talked about this in 243.
Well, it's in the textbook.
It's in every textbook, except the ones that have been printed in the past 2 and 3 years, that have started to throw it off and said, don't even worry about it. If the T distribution always works, including for low sample sizes, let's just always use it for averaging. Hopefully that makes sense. Right now, at a sample size of 30 or above, we keep scooching. Those curves are almost identical. Notice how the Z curve isn't changing right here. These values are staying fixed. But that left column is changing, getting closer to it. They're getting closer and closer and closer and closer. So technically right now, you could use either one, Z or T. But T always works, even at small samples. So the way I teach it, unlike the textbook is, many textbooks give you two sections on this. They say, if you have a sample of size 30 or above, use this. If you have a sample of size 29 or below, use this. The sample of size 30 or above says you can use either Z or T. The sample of 29 or below says you can only use T. Well, what I hear is you can always use T. Is that what you guys hear? I hear the same thing. You can always use T. Let's always use T. It makes your life easy. It gives you something pedagogical to latch onto. If I'm dealing with proportions, let's go back to the PowerPoint to end up today. If we go back to the PowerPoint, let's back up this slide right here. And you look at this bad boy, let's scoot through. When you're dealing with proportions, use the Z. And when you're dealing with averages, use the T, and that way you keep it straight in your head. That's what the researchers do. Researchers would never use Z over here. Why do they teach it? I don't know. Even your textbook does it, which I don't understand. But they do. So we won't. We'll just keep it simple. Yes? So we will get back into this on Thursday. Yes, you've had enough. I don't blame you. That's a lot to hit you with. I'll get these PowerPoints and Excel sheets up for you guys. So you can explore them if you want to. And we'll refer back to them on Thursday. Hi. Technically speaking, yes, technically speaking, because that's the, if you will, the standard error of the sampling distribution. So if you were able, Elizabeth, great question. There's actually 3 distributions floating around in your world. There's your sample and its distribution. There's the distribution of all of the samples possibly to be drawn. That's this. And then there's the population distribution, which you're never going to see. This is the sampling distribution's standard deviation, which unfortunately you don't get either, because that would require every possible sample drawn. Which you can't do because you have your population. So what we got to do is we have to say, okay, since we can't get that, that's an equal sign, not approximately, that's exactly equals. We need an approximately equals that gets us close enough. That's what we're smack dab in the middle of right now. Cool? Good, I'm glad it makes sense. Because I worry about this. This is pretty heady stuff, and there's a lot of, let's let it go off to infinity and kind of look at it. And we're taking some stuff for granted. We're taking a lot of stuff for kind of like at faith. That's why I always have those backup proofs online for you guys, because I never want you to think this is faith-based, because it's definitely not faith-based. Okay. If you show up at 12:30, we can probably make this work. Let's try it. If not, there's no rush to do it before Thursday even. We can do it tomorrow afternoon or...
The way my classes are set, I've got
very little time between. Understand. And let's not crunch it in, because I have a class that starts at 12:45 that I have to leave for like 12:25. So let's not crunch ourselves into a...
My last class was like, it's like 2:30.
I have office hours starting at 3. Look at that.
Okay, so
Today. Let's just do it then, if that works for you.
at 2:30, or do I need to wait until...
Come by as soon as you can. I might not be there, but I'll be there as soon as I can after my class is done. Cool. We'll catch you then. And it's Gabriel. We'll see you then. We'll try to make it work.
Awesome.
3 o'clock today, yes ma'am. Up at Grandview, 226. Yeah, you'll find me. Look for the picture of Van Halen and Robin Williams on my door.
Okay. Now that's a unique combination.